Tonight we're looking for distinct real-valued solutions to this system of equation that has three unknowns. X and Y are given to be irrational numbers. Y'all, that's what this set theoretic R minus Q. This literally means the real numbers, and you set theoretically subtract the rational numbers from it. And we can call it I if you want. I think I is kind of a widely adopted for irrational. Okay. Okay, now a bit about this large constant. It turns out this has a prime factorization. I'll explain that a little bit more depth of 11 times 23 23 squared. And there's a pretty famous divisibility test. If you add up these digits of the constant in an alternating fashion, you get minus 5 plus 8 minus 1 plus 9 equals to 11. Okay, and so the test is, since 11 divides 11, then that means the entire number, the entire constant is divisible by 11. And also it takes a little bit of hand calculation to determine 23 squared is the other factor. Okay, so you have only two primes in here, which kind of makes the solution process a little bit easier. Y'all notice this 11 divides 11, it would be any multiple of 11 here, including 0. If this all added up to 0, the number, this original number would still be divisible by 11. The reason for it, if you're interested, it's based on the fact that 10 raised to the n, where n is any non-negative integer, is congruent to -1. And it has to do with the parity of n, you know, as the n changes from even to odd, this goes from plus to minus here. And so this would be modulo 11. And of course, the reason why it works is because this is equal to 5 times 10 cubed, this is 8 times 10 squared, and this is 1 times 10. So this is essentially the reason why this test works. Okay, but anyway, more importantly for this problem, we know that this 4-digit constant here has a prime factorization of 11 times 23 squared. All right, and again, we're just trying to find a solution. I think there's more than one solution, but we'll find at least one and then argue that there's probably only two. Okay, so since x and y are specified to be irrational, we're going to consider these conjugate surds. And the reason is when you multiply x, y, you get the famous difference of two squares. X, y is actually equal to just a squared minus b squared. And again, a and b are understood to be integers, non-negative integers, I suppose. You get a squared minus b. Notice that since that's the square root of b, you know, you'd have a plus b times a minus b gives you a squared minus b squared, the squaring wiping out this radical operator here. Okay, so we know that xy is equal to the difference of two integers, which is nice. All right. Now, also it's given that x plus y is equal to 16. That certainly implies that a is equal to 8. Okay. Now let's just take a look at the fact this 11 times 23 squared, okay, and see what we can do with this. Well, let's write down just a little bit more. We know that a is 8, right, from this analysis right here, and so this would be equal to 64 minus b times z is equal to, and that prime factorization is 11 times 23 squared. So that's equal to 11 times 23 squared. Okay. And then just the way this is set up, folks, it makes quite a bit of sense just to equate 11 to this. Otherwise, you would have to, you know what I mean? It's more reasonable because we need for the solutions to be distinct. So we're going to go ahead and equate 11 to this first factor, okay? And see where that falls. So we'll get 64 minus b equals to 11. Right, I'm just equating this object right here with the first prime factor here. And that implies B is equal to 55. Or 53, right? B is equal to 53. Right, folks? 64 minus 11 is 53. Okay, so B is equal to 53. And so what we can get right now, knowing that A is equal to 8, we can actually write down a solution here, folks. And I'll write it in two different forms. You could write down 8 plus the square root of 53 times 8 minus the square root of 53. And then times 23 squared. Because we already did the computation up front, we can just say that that's equal to 5819. You may be going, well, don't we need a calculator? Nope. See, we know what this is equal to, right? 8 plus root 53 times 8 minus root 53 would be 64 minus 53, which is 11 times 23 squared, right? So you see, we already know from our earlier calculations, the prime factorization kind of gave us some leverage in terms of the computations we'd have to do at this stage, okay? And so what we have here is an ordered pair solution, namely 8 plus root 53, comma, it's ordered triple, okay? 8 minus root 53. And 23 squared. Okay. So this would be our x, be our y. This would be our z. Right? That would be a solution. Now, you guys, if you have time, and you're so inclined, you can. I only worked with 23 square, 11 times 23 squared. But notice we could rewrite this in this interesting way. We could write it as 11 times 23, right? Okay, separately, and then times 23 again, right? And then you could use 11 times 23 would become this constant, and then you would use 23 corresponding. I think you would end up getting, what, 11 maybe or something. But in any event, you would get another solution based on this rearranging of the prime factors. So I think there's only two solutions. I think this structure of forcing x and y to be irrational solutions, knowing that their sum was 16. See, this part's a little confusing. If you just leave this, you would be thinking, 5 plus 11, for example. But the irrational surds actually can sum up to an integer value, since the plus and minus pieces actually cancel. But anyway, folks, so that is one of the solutions. Again, I think there's another solution, but that's all. Thank you for viewing.